Hello dear students. I'm yet to receive any comments. If you can okay, Namrata says good morning sir. I think others also have joined. So let's start. I hope we can all start. Okay, so without wasting, Prerna also says good morning. Okay, good morning to all of you. So without wasting time, am I audible to all of you? First of all, I'll ask this question. Please comment first so that we'll start with the video. Am I audible? I hope so I'm audible. Okay, so without wasting time, today we will discuss with the new topic that have come. Okay, that is defects in crystal. Okay, so this is the last topic that we will discuss in this chapter. Now when we talk about defects in crystal, then we have two types of defect. One is stoichiometric defect, okay, and non-stoichiometric defect. Now see, one thing I would like to tell all of you: if you are having any doubt, please comment me immediately. Okay, I can see your comments so that I can clarify your doubts also together. Okay, so it will be an interactive session. It is not just that I am just delivering and you are just listening. Okay, so please feel free to comment so that I can see the comments and give you the suggestions of the correct answers. Okay, now when we talk about stoichiometric defect, it means where the ratio is maintained. Okay, ratio of cation and anion is maintained. And when we talk about non-stoichiometric defect, then the ratio of cation and anion is not maintained. So non-stoichiometric means it is not maintained. Stoichiometric means the ratio is maintained. I hope I am clear to all of you. Okay, so let's move on to the next part. Let's see what is stoichiometric defect. Yes. Now when we come to stoichiometric defect in a syllabus, we have two types of stoichiometric defect. Okay, one is known as Frenkel and another one is known as Schottky. Now first of all, let's understand what is Frenkel, then we will move on to Schottky defect. Okay, you can please comment also whether you are understanding or not. Now when we talk about Frenkel defect, see, this is a crystal. Imagine this is a crystal of, just imagine NaCl. So Na here is plus and Cl is minus. So Na, imagine it is positive part, and Cl, imagine it is negative part. So during the formation of crystal of NaCl like this, sometimes what happens is, see, A plus then B minus is there, A plus B minus, there is a pattern here, see, then B minus, then here it should be A plus. Okay, again B minus, A minus, A, it is a mistake here, A plus, again A plus, B minus. So a pattern is followed, but all of a sudden if you observe here, then A plus is missing from this side. Am I clear? And where is this A plus gone? It is missing its own position and it has gone in this blank space, which this is known as interstitial site. Interstitial, interstitial site. Okay, so whenever this kind of defect arises, when a cation goes out from its own position to interstitial site, then this is known as Frenkel defect. Am I clear? Now next part is the Schottky defect. In Schottky defect, if you observe, same example, think this is NaCl. See, A plus, B minus, A plus, B minus, B minus, then here it should be A plus, see, it is missing here. Again B minus, here gone, again A plus, here it should be B minus, it is missing. So in Schottky defect, you will observe that A plus, one A plus and one B minus, both are missing. Am I clear? Thank you, Namrata. So A plus and B minus both are missing, see, from their lattice side, and they are not here in this interstitial side. They are lost out from this crystal. They are not present in the crystal. So this kind of defect is known as Schottky defect. Once again I am repeating, Frenkel defect, it is lost and you will find it here in the interstitial site. But in Schottky defect, it is lost permanently from this. Okay, so these are the two kind of defects. Now why it is stoichiometric? Because the ratio is maintained. Why ratio? Because the number of positive and the number of negative ion presents, it will be equal. If you check, if you count out here, it is equal here. 1 2 3 4 5 and 6 positive, and 1 2 3 4 5 and 6 negative. Am I clear? So equal number of positive and negative ions will be missing. Here also if you observe, see, equal number or same number of positive and negative ions are present. Okay, why this is so? Because you have to maintain electrical neutrality. Solids, they are neutral. So when solids are neutral, then the electrical neutrality has to be maintained. Okay, Abrato said me something. So that means completely out of the crystal it goes. Yes, you are correct. It goes completely out of the crystal. Okay, so it is lost for him. Simran is very happy. I guess he is understanding too much. Okay, now we'll move on to non-stoichiometric defect. Now this kind of defects are also there. See, extra cation at interstitial site. Now already the name is saying non-stoichiometric. So non-stoichiometric means, see, the ratio of plus and minus is not maintained. That means either plus will be more or minus will be more. Am I clear? Now extra cation at interstitial site, the name only suggests. Look at this figure. See, what are you observing? There is m plus x minus, m plus x minus, m x minus m plus. So in this way all the sites are occupied. But if you see properly here, m plus 1 extra is present in this interstitial site. Okay, and in order to maintain the electrical neutrality, see, one electron is also present. See, one electron has to be present. Why? Because in this crystal, if a positive is more, then this crystal will become positive. Okay, so in order to make this crystal neutral, you need one electron. Am I clear? You need one electron. Done. So this is known as non-stoichiometric defect, where there is extra cation at interstitial site. Okay, next part is, see, anion vacancies. See, anion vacancies means, see, there is one crystal structure and one m plus x minus, there is m plus x minus, x minus m plus. Now there should be one x minus, but one x minus is missing. Okay, so when this is missing, that means this solid again becomes positive. Am I clear? In order to make it neutral, what will happen is one electron will come and occupy this space, and this point is known as F centered. Why F centered? Because this electron will impart color. Am I clear? This electron will impart color to this compound. So whenever you have free electrons like this, then what you will observe? You will observe color. Am I clear with anion vacancies? Please do comment. Fast. I hope I am clear. Okay, so next topic is, we have the last topic, that is doping. When we talk about doping, it is for, okay, yes sir, fine. Now when we talk about doping, then it is for silicon. Okay, now silicon is a semiconductor. So doping process is done to increase the conductivity of a semiconductor. Once again I am repeating, doping is done to increase the conductivity of a semiconductor. So silicon I have taken, say silicon. Now what is doping? Doping is introducing element. See, silicon belongs to group 4. So when you dope, you introduce either element from group 5 or you introduce element from group 3. Am I clear? So in n type doping, you are introducing from group 5. So arsenic belongs to group 5. Am I clear? That means I can say arsenic has 5 electrons. Okay, so look at this situation. Now arsenic has 5 electrons, so one is shared here, one is shared here, one is shared here, one is shared here, one extra is there. See, free electrons. What will happen to this free electron? This free electron can move from this one space to other space. It can move from here to here, it can move from here to here, it can move from here to here. That means due to doping, the free movement of electron is increased. So whenever there is free movement of electron, what increases? Electrical conductivity increases. Am I clear? So doping is done to increase electrical conductivity. So here arsenic is helping silicon to increase its conductivity by giving this free electron, which can move from here to here. Am I clear? Free electron means more conductivity. This thing I think all of you know about it. Okay, now next type of doping that we have is the p type doping, the positive type. So in case of positive, we will take elements from group 3, that is we have taken from boron here. See, See, altogether boron, one is silicon, one silicon bonded. See, boron has 3 electrons, so one here and one here. See, one more silicon is there, but boron does not have any electron to share with the silicon, so a hole will be created here. Am I clear? So as soon as this bond comes to know there is a hole creation here. Okay, let me see. Sir, any element of group 5 you can use? Yes, you can use any element of group 5. Okay, Abratos, and Namrata is saying, does that extra moves out? No, it doesn't move out. It moves in the interstitial site. Once I'll say you, it moves here in this and in this interstitial site. It keeps moving here. Okay, Namrata. Now, okay, boron. See, 1, 2, 3 bond with silicon, but one bond it is not able to form because it doesn't have electron. So a hole means a blank is created here. So as soon as this bond means 2 electron, it comes to know, it will try to come in this blank. Okay, again one blank will be created here. Again this will come to know, this will come here. Again one blank will be created. So what is happening is continuously a hole is created, and in order to fill that hole, electron is moving. Okay, so this hole is actually doing nothing but increasing the movement of electron. Am I clear? So if this increases the movement of electron, then what happens to electric conductivity? The electric conductivity also increases. I hope I am clear to all of you. The electric conductivity increases. See, hole is created. So in order to fulfill this hole, electron moves. Okay, again one hole is created, again electron moves, again a hole is created, again electron moves. So in this way electron keeps moving and filling the hole, so electric conductivity increases. Thank you, Simran. Okay, the last part is, see, properties of solid, electric property and magnetic property we have. See, 2-3 definition. What is pyroelectricity? Okay, what is piezoelectricity? What is ferrimagnetic substances? What is anti-ferrimagnetic substances? I request all of you to learn the definition and one example that is only going to come in either exam. Am I clear? So with this part we end solid state today. Okay, I hope I am able to make it clear to all of you. I thank you all for watching my video. Please do subscribe my channel, share this video, and don't forget to like this. Okay, thank you all, my dear students.